Okay, we're going to do one last example now. This is a linear constant coefficient ODE where the right-hand side has a discontinuous function in it, but in this case it's a step function rather than the delta Dirac function. Now, this right-hand side is not so terribly complicated. Other than the fact that we're multiplying by 13, which only affects the amplitude. What we have is this. This function starts at 1 until you get to time 1. And then at time 1, this one turns on, so you have 1 minus 1 equals 0. So this drops down to 0 at time 1, and it starts at 1 on the interval from 1 to 0. So also in this case the initial conditions are 0 and 0. So this is a quiescent system, and but it has a constant input. So mass spring, that would be like a constant force applied to the mass. Or in a LRC circuit, this would be a voltage being applied to the circuit. But it would mean what? The capacitor was fully charged, so we no longer have any current. So here's our equation, and we'd like to solve this by the method of Laplace transforms. As a matter of fact, we have no choice but to solve it by Laplace transforms, because this is a discontinuous function and our other techniques do not apply to those. So what we're going to do is transform the left-hand side and take into account that these terms are 0, so this simplifies a little bit, and you'll be glad for that by the time we're done here, because this is not so simple to work out, even with this extra nice starting conditions. So when I take two derivatives on y, its transform is s squared cap y minus sy at 0, which is 0, minus y prime at 0, which is also 0, and similarly for those other terms. So we end up with this times cap y at s is equal to 13 times the transform of this function here. Well, the transform of 1 is 1 over s, and the transform of ut minus a is e to the minus s over s, and I got a 13 on that as well. So there's our transform function, and we simply need to divide both sides by this, and it looks like we're making great progress here, and we are. So we have, let's see, how shall we put this? 13 over s from here times s squared minus 6s plus 13. And then if you factor 13 over s off from this, you'd have left 1 minus e to the minus s. So we're going to take the inverse transform of this fraction times 1, and then we're going to have to take the inverse transform of this times e to the minus s. Of course, that's not so difficult. That is involving a shifting theorem, and we know that if we have e to the minus as as a factor on cap f of s, then we just go back to a shifted form, ut minus 1 times f of t minus 1. So we really just have to do this, and then we write it down twice, once without a shift and once with. So how are we going to handle this thing? Well, it doesn't take for too long to figure out that this thing is not going to factor. 13 is prime. There's no way you can get that middle term, so that would have to be done once it's by itself by completing the square. But it's not by itself, is it? So what we need to do first is take this, this fraction and split it into two fractions, a constant over s. Now you just have to write these so that they're proper fractions. So we have s squared minus 6s plus 13. Well, this is second degree, so this potentially could have both first degree and constant terms in the numerator. Now, I should say there is one other way of doing this, and that is you could take the inverse transform of that much, and then since there's an s in the denominator, you integrate it once. Integrate it on the interval from 0 to t. It turns out that isn't so nice in this case, because this has, we're going to complete the square, so that means you're going to get an exponential times a sine or a cosine. And integrating those requires using parts twice. So even though it would be a perfectly valid way to solve the problem, and if you like to do it that way, it's fine. I just think that even though this is going to require a lot of algebra, it's probably easier than doing it with the integration trick. The other reason I'd like to do it by partial fractions is that it's going to allow me to show you some tricks with partial fractions that perhaps you haven't seen, or at least you haven't seen in a while, so it's good to be reminded. Now, when you put these back together, of course, this one you multiply top and bottom by the quadratic, a times s squared minus 6s plus 13, and then plus b, I wrote bc. Really, what I wanted there was bs. It is the variable is s. bs plus c. So bs plus c times that s all over the common denominator. So that's just that. So we have these two fractions equal to each other. Their denominators are equal, so their numerators are equal. And that gives me this equation, a times the quantity s squared minus 6s plus 13 plus the quantity bs plus c times s. And I really wanted to do this because I'd like to show you kind of a slick trick. Now, what I said earlier was, there is one way to do this, which is to multiply all this stuff up. You gather up the s terms, you gather up the s squared terms, and gather up the constant terms and equate them to what's over here, which, by the way, are pretty simple. 0s squared plus 0s plus 13. And, really, that's not so bad here. You can do it. You can do it rather quickly. In some cases, there's only one s squared term, right? So as squared has to be equal to 0s squared. Therefore, a has to be equal to 0. Oh, false. We'll edit that out. It's actually, you can do it by a system of equations. We have as squared and we have bs squareds. So a plus b must be equal to 0. And for first degree terms, we have minus 6a plus c. So minus 6a plus c is equal to 0. And likewise, the constant term comes just from here. 13a equals 13, so a must be 1. So you can do it. There's nothing wrong with that. But I want to use another technique just so that you are aware that it's possible to do it. And the technique I'm about to use oftentimes really simplifies things. In this case, it probably does not make it better. But if we had, say, like this, we had this one s cubed or something here, and that thing squared. The technique I'm about to show you would dramatically simplify the work. So what I'm going to do is my usual trick. First, I notice that if I set s equal to 0, I can knock out both the b and the c, and that will allow me to compute a. So on the left-hand side, I have 13, and on the right-hand side, if s is equal to 0, I've got 13a. And this is just 0. So that tells me that a equals 1. And I'm going to go ahead and plug that in because that'll give me a little bit simpler form to work with in the SQL here. Okay. Now, I would like to know what B and C are. We could compute B directly from algebra if we wanted to, but here is a slick trick for cleaning these things up. S squared minus 6s plus 13 plus, I'm going to multiply this out here because it will make the next step easier. It's not required, but it is nicer. So just distribute that s, and now we're ready for the trick. Now you think, well, what could I possibly plug in for s that would knock out the b but not the c? Well, nothing, because this has an s squared and that has an s. The 0 that would kill this would also kill that. Well, there's an easy fix. Remember, this is one polynomial is equal to another, so their derivatives are equal to each other. I'm going to take the derivative of both sides. 0 equals 2s minus 6. Derivative of 13 is 0. Taking derivative here, I get 2s times b, 2bs plus c. Now, go ahead and set that s equal to 0 in this derivative form, and I've got 0 on the left-hand side. That goes to 0. Minus 6 plus 0 plus c. Aha, c must be 6. Not so bad. And, well, if it worked once, it ought to work again. Let's take another derivative. Derivative of 0 is 0. Derivative of 2s is 2. That has derivative 0. This has derivative 2b. And c is a constant. So when you take its derivative, it's 6 actually. But when you take its derivative, it's 0. And in this case, I can now see b quite easily must be equal to minus 1. So I've got a, b, and c, and I didn't have to solve a system of equations. I didn't have to do a bunch of algebra multiplying all this stuff out and gathering up like terms. I just take derivatives to clean this up. So I now know the partial fraction decomposition. 13 over s times s squared minus 6x plus 13 is equal to a. Well, a is 1 over s, plus b. B is a negative 1. Plus a negative 1 times s plus c, that's a 6 over s squared minus 6s plus 13. So there's my fraction split into fraction with a linear denominator and a fraction with a quadratic. Last step, let's just clean this up a bit. This, we know, we're going to have to complete the square on that. So why don't we do this? I'll put a minus out here and call this s minus 6. And then down here, I've got s minus 3 squared. Half of 6 is 3. So now that has effectively added 9 to those. 9 plus, so I need to subtract off 9. So 13 minus 9 is 4, which is 2 squared. And we're almost there. 1 over s minus, now that I would like to have as s minus 3. S minus 3, well, it's s minus 6, right? So s minus 3 minus 3 over s minus 3 squared plus 2 squared, or 4. Copying from here. Okay, so there's my function split, and split in a way that makes it relatively easy to do the inverse transform. So let's get this copied over to a new page, and we'll get on with the work. So we know that cap y at s is equal to this kind of complicated fraction, but it's all fixed up now to work nicely. So I'm going to write this as, here's where I'm copying from. So I'm going to write this as minus s minus 3 over this stuff, and then plus 3 over this stuff. So minus the fraction s minus 3 over s minus 3 squared plus 2 squared plus 3 over s minus 3 squared plus 2 squared. Okay, and that is being multiplied by the quantity 1 minus e to the s. E to the minus s. Okay, well, here we go. The first thing is we have 1 times this, and we want to take its inverse transform. Well, the inverse transform of 1 over s is 1. Then the inverse transform of, well, if we had s over s squared plus 4, the inverse transform of that would be cosine of 2t. But we've shifted on the s-axis by 3 units to the right. So we need to multiply by an exponential on the t-axis of e to the 3t. All right. Now, we have a similar thing here with this exception. We really need a 2 up here, so factor the 3 out, multiply the top by 2, and then divide the top by 2. So that would put a 2 up here, and then this is e, or rather e, this is sine of 2t, and it's shifted, so it's multiplied by e to the 3t. Okay, so 1 times this has this inverse transform. And now this tells me it's the inverse transform of all this. Well, fortunately, we have that written out, but we just need to shift it by 1 unit on the t-axis and multiply it by corresponding unit step function. So this is minus ut minus 1 times all of this shifted to the right by 1 unit. Actually, I regret writing that bracket right there, because I can see that I have an e to the 3t that's common on these, so why not factor that out? This is complex enough as it is, but now I'm shifting by 1 unit. And then I have left my linear combination of cosine and sine. So the cosine is negative. Why don't we write the sine first then? Sine of 2 t minus 1 minus cosine of, oh, and that sine's got a 3/2 on it, cosine of 2 t minus 1. So there it is. A pretty complicated function. However, you can see this though. Take a look. We have we're missing a bit. Missing the 1. So it's ut minus 1 times all of this shifted, which we have, but it's also minus ut minus 1 times the 1. So I could add it. Doesn't really change the value, but it makes it easier to tell where it came from. All right, now if you go back to the original ODE, it was supposed to be a system that was quiescent, and then at except, well, it started as quiescent, but it had a constant force on it. So that force would begin to move the system away from static equilibrium immediately at 0. So it begins to move under this force, and then at time t equals 1, that force is turned off, and we would expect then to see some shift in the response of the system. So let's see here. You do notice some stuff here. First of all, to the left of t equals 1, all of these terms are 0. So you just have this, and sure enough, it does tend to move in the appropriate direction, and then as we cross that boundary t equals 1, we can see, well, you notice this 1 gets subtracted out, and that's probably from the force of that's dropping off, and then we have some additional terms that come in. A different sinusoid will combine with this, and of course it will create yet another sinusoid, but it's a different one than we had at the first part of the solution. So intuitively kind of makes sense, and that's the solution of our system. So there's our solution cleaned up just a little bit, and there's just one last thing I'd like to comment on, and that is, if you notice this, we've got a sinusoid here, and the same one shifted. The constant gets subtracted out after t equals 1, corresponding to the original force dropping out after t equals 1, that input force. Um, but there is something that potentially could be a little bit troubling, and that is we have e to the 3t and e to the 3t minus 1. Those are exponentials that grow. So the question might be, well, hold on. If this were a mass spring system or a LRC circuit, how is it that the response of the system is growing exponentially? It's not a case of resonance, because resonance will give you generally a linear term out here. And the answer is really quite simple. The answer is simply that this equation was chosen to have certain features in the solution, not to be a realistic one. If you were thinking of this as, say, a mass spring system, this is the damping term right here, or if it were an LRC circuit, this is the resistance term right here. Well, this has negative damping, or you could say negative resistance. So in other words, as the velocity of the oscillating mass increases, the damping, so-called damping, doesn't act to slow down the system. It acts to speed it up. Well, there is no such system as a real physical. It can't be realized as a physical system. So that's why we have this growing exponential here, and we could come up with cook-up cases where it's different, but the algebra wouldn't work out quite so nicely, and this one was tough enough. So that's how we ended up where we did, and that completes the discussion of how to solve ODEs with discontinuous inputs by the method of Laplace transforms.